Students, welcome to a class of topology. In this video, we are going to discuss about base for a topology. Okay, suppose we have a topological space. Let X2 be a topological space. Okay, then base for a topology is actually a collection B, which also consists of some subsets of X, subsets of X. This collection is actually a subfamily of tau. B is a subfamily of tau. Is called base for tau. Is called a base for tau. Base for tau if every member of tau can be expressed as union of some members of B. Can be expressed as union of some members of tau. Union of some members of tau. This is the definition of base for a topology. Some collection of subsets of X, that is a subfamily of tau, is called a base for tau if every member of tau can be expressed as union of some members of tau. That is, for every A belongs to tau, A can be written union of B in script B. Collection Bയിലെ മെമ്പേഴ്സിൻ്റെ യൂണിയൻ ആക്കിയിട്ട് നമുക്ക് ടോയിലെ മെമ്പേഴ്സിനെ റെപ്രസെൻ്റ് ചെയ്യാൻ പറ്റുമെങ്കിൽ ദാറ്റ് കളക്ഷൻ സ്ക്രിപ്റ്റ് ബി ഈസ് കോൾഡ് ടോപ്പോളജിയുടെ ബേസ്. ഓക്കെ, ദിസ് ഈസ് ദ basic definition of base for a topology. Now, let's see some basic example for a base. Consider discrete space. Discrete space X with the topology 2D. Okay, I consider collection as set of all singleton X, X varying over capital X. I can prove that this collection, I am going to prove that this collection is a base for the discrete topology. I will prove script B is a base for 2D. So to prove that every member of 2D, that means every open sets in this topological space X 2D can be written as union of members of script B. And what are the open sets in this topological space, or what are the members in this topological space? Topology 2D is a power set topology, so every subset is open in this topological space. Since every subset of X is open, let A is an element in tau means A is a subset of X only. Okay, then we have to prove that A can be written union of members of B. We know that for any set A always can be written union of singletons where X is a member in A. അല്ലേ, എയിലുള്ള എല്ലാ എലമെൻസിനെയും സിംഗിൾട്ടൺസ് ആക്കി എഴുതി അവരുടെ യൂണിയൻ എടുത്താൽ വി ഗെറ്റ് എ ഓൺലി. സോ എ ക്യാൻ ബി റിട്ടൺ ലൈക്ക് ദിസ്. സോ വാട്ട് ഈസ് സിംഗിൾട്ടൺസ്? ഈ സിംഗിൾട്ടൺസ് ആർ ദ മെമ്പേഴ്സ് ഇൻ സ്ക്രിപ്റ്റ് ബി, കറക്റ്റ്? സോ ദിസ് എ ക്യാൻ ബി റിട്ടൺ യൂണിയൻ എക്സ് ഇൻ എ ബി എക്സ് വേർ ബി എക്സ് ഇസ് ഈക്വൽ ടു സിംഗിൾട്ടൺ എക്സ്. I call singleton X at Bx. I denote Bx by the singleton X. Then A can be written union X in A Bx. Then what is Bx? Bx is a member in B, correct? Then A can be written union X in A Bx where each Bx R belongs to script B. So script Bയിലെ എലമെൻസുകളായ BXകൾ എന്ന് വെച്ചാൽ സിംഗിൾട്ടൺസ് ഉപയോഗിച്ച് നമ്മൾ എനെ റെപ്രസെൻറ്റ് ചെയ്തു. Correct? So A can be written as union of members from script B. That means every member of tau can be written like this. Therefore, this collection script B is a base for discrete topology. which implies script to B is a base for 2D, base for discrete topology. And it is not easy to verify this definition for every case. Therefore, we need a characterization that we call it as a theorem. Okay, we will prove characterization of base as a theorem. Let X2 be a topological space. Let X2 be a topological space. A subcollection script B of tau is a base for tau if and only if for every x in X and any open set G containing small x, comma, there exists some B in script B such that X belongs to B and B is contained in G. This is the characterization of base for a topology. What is this actually? When you have a topological space X2 and we have a collection script B as a base, script B is a collection of some subsets of X, okay? Tau is here, B is here, okay. Then this subcollection B is called a base if you take any point in this topological space and you take any open set G containing small x, where G is a member in tau. Then there should exist some member in B, script B such that X belongs to B and that B is contained in B. This B is in script B. So X belongs to B and that B is contained in G. So if you take any open set G of small x, in between them there should exist a member from script B. This is the characterization of base for a topology. Okay, we will see the proof. Assume collection B is a base for the topology tau. We have to prove that this script B has the required property of the theorem. Okay, for that I take an element. Let small x be an arbitrary element in capital X and capital G be an open set of small x containing the small x. Okay. Since G is an open set, what is the definition of open set in topological space? Members of tau are called open sets. When G is open, G, X belongs to G, and what is G? G is a member in tau. By the definition of base, when script B is a base for tau, every member of tau can be written as union of members of script B. So by definition of base B, there exists G can be written union of members of B in script B. Okay, right. What you want to prove? When you take some element and an open set containing that element, in between them there should exist a base element. That is our concern. So we need to find out a base element. Okay. Now what we have, G can be written like this union. And what is G? G is a set containing the element small x, correct? When X belongs to G and G is equal to this union, X also belongs to this union. So X belongs to G and G is equal to union of B. B in script B implies X automatically belongs to this union. B in script B. That means X belongs to union of these B's means X should belongs to B for some B in script B. Then only it belongs to their union for some small b in script B. Okay, So what you get, when you take an element small x and an open set G containing small x, in between them there exists a base element B. What is this B? This B is actually belongs to this union, one among these elements from script B. Therefore this B, capital B, will be contained in the collection script B. So what you get now, x belongs to this small b and this b is really belongs to our collection B. Correct? And also this script B and this B is actually contained in union of B also. So what can you say about, and what is this union? This is nothing but our G. So what, x belongs to B and that B is actually contained in G. So we get the required property. Okay. Now the converse part. Conversely assume this condition and we have to prove that script B is a base. Conversely assume the condition okay. We have to prove script B is a base. Here we have to verify the basic definition. For that, let G be an arbitrary open set. It's an arbitrary member in tau. We have to prove G can be written union of members of script B. When G belongs to tau, actually we can only apply our given condition, that is for every small x and an open set containing G. ഇപ്പോൾ നമുക്കൊരു എലമെൻറ്റും ഒരു അതിനെ കണ്ടെയ്ൻ ചെയ്യുന്ന ഒരു ഓപ്പൺ സെറ്റും ഉണ്ടെങ്കിലേ നമ്മുടെ തിയറത്തിലുള്ള കണ്ടീഷൻ നമുക്ക് അപ്ലൈ ചെയ്യാൻ പറ്റുള്ളൂ. സോ ഫോർ ദാറ്റ് ഐ ടേക്ക് an element from G. Let small x is an element in G. Then small x belongs to capital X and G is an open set containing X. Open set containing small x. Now we have the element and an open set containing it. Therefore we can apply the condition of the theorem. So then by assumption there exists some b in script B such that x belongs to B and that B is contained in G. By assumption. Okay. Now for every x belongs to G, we will get some B. So this B is actually varying with respect to our small x. Correct? So I call this B as Bx. Ready? Corresponding to every x in G, we will get some Bx. Correct? Now then G can be written as union of singleton x in G. This can be written as this is actually true for every set. So which is equal to union x varying over G. When corresponding to every x in G, we get some Bx. Correct? Therefore instead of singleton x, I write it as Bx. Okay? And where this Bx came from? This Bx is actually got from the definition of base. Therefore G can be written union x in G Bx. And what is this Bx? Where Bx is a member in script B and Bx is contained in G. This is we know. So now what you get now? G is equal to union of members in script B. So every member in tau can be written like this. Therefore script B is a base for tau. So using this characterization, we are going to prove some base for real and with the usual topology. Okay. Consider real and with the usual topology. 2u. Okay, usual topology is denoted by 2u. And I take B as collection of all open intervals AB of the form A comma B in real line where A less than B. Then this collection script to be consists of subsets of real line only of the form open intervals, and this script to be is a base for the usual topology. To prove this, we are going to use the characterization. What is the characterization? Script to be is a base for tau if for any element in the set and any open set containing that set, in between them there is a base element. Correct? So for that, let small x is an element in our capital X. Capital X is here real line. And G be an open set in real line such that x belongs to G. X ne contain ചെയ്യുന്ന ഒരു open set G യും എടുത്തു. Okay. Then actually we need to find out a element in between the element and the set G from script to B. Right? Since G is an open set and X is an element in G, then what can you say about what is G is an open in means? Which implies G is nothing but member in tau u. When G, what is tau u? Tau u is collection of all A subsets of R such that for every A in A there exists R greater than 0 such that interval of the form A minus R, A plus R contained in A. This was the definition of tau u. Here G is a member in tau u. Then for every small element in G, it has this property. So small x is an element in G. Therefore this element has this property. Since x in G, there exists some R greater than 0 such that interval of the form x minus R, x plus R will be completely contained in G. Correct? X minus R, x plus R will be contained in G. Now, what is x minus R? X is a real number, R is a real number, x minus R, x plus R are real number. Let A equal to x minus R and B equal to x plus R. Then this interval is AB, of the form AB. Okay? And this clearly this interval contains, what is this interval actually? Here is x minus R and x plus R. X minus R, x plus R are, x is in between x minus R and x plus R. Therefore, this interval clearly contains the element small x. Therefore, x is an element in open interval AB, where A belongs to x minus R, A equal to x minus R, B equal to x plus R, and this open interval is contained in G. So, in between the small element and the open set containing that element, there is some open interval AB. Where this open interval AB belongs to? It belongs to our base script B. So, in between the element and an open set G containing that element, we get an element from script B. This open interval AB is a member small b in script B. So, we get the condition or we get the characterization of base, which implies script B is a base for usual topology. Tau u. Another example, consider the metric space. We know that every metric space XD is a topological space. And what is the topology here? The metric topology, tau. And what are that? It's just a subset of X such that A is open with respect to the metric D. Metric D. A is open with respect to the metric D. That means the interior point definition. Okay. So, we are going to define a base for metric space. Take B script B equal to collection of all sets of the form BD of XR, where X varying over our capital X. R is a small positive real number. Okay, this is actually definition of what is BD of XR. BD of XR are elements of Y such that D of XY is less than R. That means this is our space X. For any point X in X, we consider some radius R, and in elements which are belongs to this neighborhoods are belongs to BD of XR. Okay, we can prove that this script B is a base for tau. For that, we need to verify the characterization. Let small x be an element in capital X and G be an open set containing small x. Okay, so we in between them we need a base element. Okay, since G is open, G belongs to our top. What is our top? Metric topology, which implies G is open set in the metric space XD. When we say that a space is a set is open in a metric space, G is open as a in a metric space implies all points of G are interior points. All points of G are interior points. What is the meaning of interior point? A point is said to be an interior point of a set in a metric space if there exists at least one neighborhood of that point which fully contained in G itself, which implies for every small x in capital G, there exists some radius r greater than 0 such that the neighborhood BD of XR, the open ball BD of XR is completely contained in G. This is the definition. So, the neighborhood BD of XR always contains the center point X, correct? So, X belongs to BD of XR and that BD of XR is contained in G. So, in between the point and the open set containing small x, there exists some BD of XR. Where this BD of XR belongs to? It belongs to our collection script to B. So, in between the point and an open set containing it, there exists a base element. Therefore, this collection script to B satisfies the condition of characterization of base. Therefore, script to B is a base for metric topology tau.